Okay, so now let's discuss comparisons, masks, and Boolean logic. So now this lecture and upcoming lectures covers the use of Boolean masks to examine and manipulate values within the Numpy arrays. Masking comes up when you want to extract, modify, count, or otherwise manipulate values in an array based on some criterion. For example, you might wish to count all values greater than a certain value, or perhaps remove all outliers that are above some threshold. In NumPy, Boolean masking is often the most efficient way to accomplish these types of tasks. We will start with the example counting rainy days. You can get the data, the CSV data, from the link I'm going to show here. This is the link raw.github user content. We will use JQueDP Python Data Science Handbook, Master Notebooks, Data, and Seattle 2014.csv. So let's continue. Imagine you have a series of data and just go to the file, save that with the CSV. It will automatically save as the CSV. So imagine you have a series of data that represents the amount of precipitation each day for a year in a given city. For example, here we will load the daily rainfall statistics for the city of Seattle in 2014 using pandas. Let's import numpy as np, then import pandas as pd. Using pandas to extract rainfall inches as a numpy array. Rainfall equals to pd dot read csv desktop, as I've saved the file in desktop, Seattle 2014.ss3 in the square brackets prcp precipitation dot values. Inches, we want that in inches. Rainfall 254, that is 1/10, 1 by 10 mm is equal to, we have to convert it into inches. Inches dot shape, that results in 365. So the array contains 365 values giving daily rainfall in inches from January 1st to December 31st, 2014. As a first quick visualization, let's look at the histogram of rainy days we will make, which was generated using matplotlib. Matplotlib, import matplotlib.pyplot as plt. Now let's import seaborn.sct, set plot styles. Now plot hist 40. Now you can see here the graph, the histogram. So the histogram gives us a general idea of what the data looks like. Despite its reputation, the vast majority of days in Seattle saw near zero measured rainfall in 2014. But this doesn't do a good job of conveying some information we would like to see. For example, how many rainy days were there in the year? What is the average precipitation on those rainy days? And how many days were there with more than half an inch of rain? So let's dig into the data. We will discuss digging into the data. One approach to this would be to answer these questions by hand, like loop through the data, incrementing a counter each time we see values in some desired range. For reasons discussed throughout this section, such an approach is very inefficient, both from the standpoint of time writing code and time computing the result. So we saw in earlier in the universal functions that NumPy's ufuncs can be used in place of loops to do fast element-wise arithmetic operations on arrays. In the same way, we can use other ufuncs to do element-wise comparisons over arrays, and we can then manipulate the results to answer the questions we have. We'll leave the data aside for right now and discuss some general tools in NumPy to use masking to quickly answer these questions, these type of questions. So now let's discuss comparison operators as ufuncs. So in universal functions earlier, we introduced ufuncs and focused in particular on arithmetic operators. We saw that using plus, minus, multiplication, divide, and others on array leads to element-wise operations. NumPy also implements comparison operators such as less than and greater than as element-wise ufuncs. The result of these comparison operators is always an array with a Boolean data type. All 6 of the standard comparison operations are available. Now let's start. X is equals to np dot array 1 2 3 4 5 with the bracket square bracket 1 2 3 4 5. Now x is less than 3. That results in true true false false false. Now x is greater than 3. This results in false 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 true true. And now less than or equal to 3. That results in true 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 false false. And now that results in this results in false false true true true. Now this means not equal true true false true true. Now this means equal x. This results in false false true false false. So it is also possible to do an element by element comparison of 2 arrays and to include compound expressions like this. Array false true false false false. So as in the case of arithmetic operators, the comparison operators are implemented as ufuncs in NumPy. For example, when you write x is smaller than 3, internally NumPy uses np.less x comma 3. A summary of comparison operators and their equivalent ufuncs are shown here in the table here. You can see. So just as in the case of arithmetic ufuncs, these will work on arrays of any size and shape. Here is a 2-dimensional example. RNG is equals to np dot random dot x is equals to we made an error here. Let's look at and fix that error. RNG rand int. This results in 5033, a table, and now x is more than 6. This results in true, 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 false, 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 true, 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 for true, false, false. So in each case, the result is Boolean array, and Numpy provides a number of straightforward patterns for working with these Boolean results. Now working with Boolean arrays. So given a Boolean array, there are a host of useful operations you can do. We'll work with X, the two-dimensional array we created earlier. Print X 503379352476. Now counting entries. To count the number of true entries in a Boolean array, np.count underscore non-zero is useful, like here. How many values less than 6? Now np.count non-zero. That results in 8. So we see that there are 8 array entries that are less than 6. Another way to get at this information is to use np.sum. In this case, false is interpreted as 0 and true is interpreted as 1. Like this, np.sum. Gives this results in 8. So the benefit of sum parentheses is that with like other NumPy aggregation functions, this summation can be done along rows or columns as well. And so how many values less than 6 in each row? np dot this counts the number of values less than 6 in each row of the matrix. So if we are interested in quickly checking whether any or all the values are true, we can use, yeah, you guessed it right, np.any or np.all. So, are there any values greater than 8? np.any. This results in true. And are there any values less than 0? np.any. False. Are all values less than 10? np.all. Are all values equal to 6? np dot false. np.all and np.any can be used along particular axes as well. For example, are all values in each row less than 8? Now, sorry. Axis equals to 1. Array true, false, true. So here are all elements in first and third row are less than 8, while this is not the case for the second row. So finally, a quick warning, as we mentioned in aggregations, minimum, maximum, everything in between earlier, Python has built in sum, any, and all functions. These have a different syntax than the NumPy versions, and in particular will fail or produce unintended results when used on multi-dimensional arrays. Be sure that you are using np.sum, np.any, and np.all for these examples.